The little box is off. All right. My name is Michael McDougall. I'm going to talk to you about a research project we're starting at Grammatech called the Code Awareness Assistant. This is being funded by the United States Navy. Of course, any opinions I give are not the opinions of the U.S. Navy. All right, so I'll start by telling you a little bit about Grammatech. We're a small business centered in Ithaca, New York, and our focus is on software analysis and manipulation, founded by a couple of professors. One is emeritus at Cornell. The other, Tom Reps, is at University of Wisconsin. And Grammatech does a combination of computer science research and product development. And the research, this is typically sponsored research by government agencies, such as we currently have projects under NASA, a bunch under DoD, NSF, and we occasionally get some commercially sponsored research projects too. And the focus of these research projects are static and dynamic software analysis, and that's including analysis of both source code, usually C, C++, and machine code. And there our focus is mainly x86, but we're expanding to ARM and PowerPC and some other architectures. And so we build general analysis tools and technology and then try to apply them to particular problems. And those problems are typically enhancing safety and reliability in systems, making it easier for developers to build safe and reliable systems, increasing security of software, and producibility. And this is kind of a general word denoting making sure that when DoD or someone sets out to build a big piece of software, they can actually get that accomplished within budget and with the quality that they desired. In terms of product development at Grammatech, we've got two products right now. One is Code Surfer and one is Code Sonar. Code Sonar is one of these static analysis tools that you've been hearing about over the last couple days. In particular, it was used to check the MSL flight code for both bugs and risky code and compliance with the JPL coding standard. We do have a booth outside, and Curtis is manning that booth. And if you want to talk to him, or if you want to learn about the static analysis tool, you should talk to him. He's got some white papers, and he can, I think, probably give you a demo. I'm not going to talk about the static analysis product in my talk. I'm going to be talking about this research project that I'm starting up. Although the two are related, and I'll mention how that works later on. This is just a quick flash of a bunch of logos for some of the Grammatech customers. And you can see up at the top is the Mill Aerospace domain, and there's a bunch of, I think, overlap with attendees here in the workshop. From a commercial point of view, this hopefully gives you some legitimacy in terms of there are actually people using our tools. As a researcher, what this says to me is I can draw upon a lot of experience that we have in dealing with real code that's out there and use that to help kind of drive and ensure that any tools that we come up, any software engineering tools and approaches that we are coming up with in our research efforts really do address software as it is written in the real world. Okay, so a quick outline of the talk. I'm going to start with kind of a small code example and kind of walk through some of the characteristics that we want the tool to identify. And then I'll talk about detailed design decisions in general, and then various aspects of that. Talk a bit about how the tool is going to work. And then at the end, I'm going to kind of do a call for participation. Hopefully some of you will be able to act as guinea pigs, or at least give me requirements and needs based on your experience working with software in the spaceflight domain. All right, so this is another programming quiz, like you've seen a bunch already. So this is a pretty simple procedure, just swaps two integers. So can anybody give me something that's wrong here? What's a problem with this procedure? Pardon?
There's lost assignment. It's a black hole. Lost information.
So where do I lose the information?
So you assign to the TMP and don't use it.
Oh, you're right. There's a bug. Oh. That's funny. I had that. Well, that's embarrassing. But
Where can we send our bill?
yeah. So I fixed that in another branch of these slides. And then all right. So I think when I was editing it, I probably gave you the example. But so even in this, so that shouldn't be star temp. For the sake of moving on, let's. So there's a problem here where there's a potential null pointer dereference. If somebody passes in an X that is null, and it's a little subtle in that it's not inherently bad. So the code as written, as long as you never call it with null, it's going to work and it's going to do its job. So you'll often run into developers who say, look, I don't want to do any kind of error checking here. I know I'm going to call it in a situation where it's used correctly. The callers know what the limitations of the code are. I don't want to worry about this. And we've seen this even in mission-critical spaceflight code. For example, the code sonar static analysis tool will not warn you about a potential null pointer dereference here, just because this pattern is so common in code that developers will ignore those warnings. So the question is this an accident waiting to happen, or is it a prudent optimization? And it really depends on the context. That said, when I go to call this procedure, I want to know the property that it doesn't handle null. And if I'm in a situation where I'm working with pointers that may be null, I'm going to have to insert an error check on my own right there. And now, whether it was a prudent optimization or accident waiting to happen partly depends on what's happened recently in the code. So if I look at through my version control system and look at what happened last week, and I see that it used to have an error check, that's a big red flag. That's a warning that something significant in this interface has changed. Previously, it handled null pointer arguments, and now it doesn't. And so if there was code before that relied on that and assumed that the procedure would not crash when passed a null argument, that code is now likely to cause a crash. And so when you see this, accident waiting to happen or prudent optimization, this looks like an accident waiting to happen. And so this is another piece of information that I would want to know when I'm working with this code. And so once I understand that, there's a number of, once I've observed these properties of the code, there's a number of things I can do. One is I can handle the error by maybe reinserting something that existed before, or inserting a new error handling clause, as in the first example here. Maybe I don't want to do that. Maybe I understand, or I want to avoid the computational cost of that validity check at the start of the procedure. At the very least, I should document the fact that this is kind of a fragile procedure that may crash in certain circumstances. So another option is to add some documentation. A third option is to add some assertions to the code. This is useful because it both functions as documentation for any developers looking at the code. They'll know that the intent was to assume these preconditions, this particular constraints on how the procedure should be used. Plus, you get some dynamic checking, at least in a debug environment, and depending on if you leave assertions on in your deployed code, you'll get at least some sort of crash report if you do encounter that situation. And so these are the kinds of things that we want the code awareness assistant to do. So when faced with code like this, ignoring the typo I had that's now propagated itself across all these slides, ignoring that issue, I want my code awareness assistant to kind of act like an expert programmer sitting beside me and looking at the code, programmer that knows the history of the code, knows all the implicit constraints and design decisions that went into that code, and can say, you have to watch out here. This code is unsafe. if X or Y is null. B, not too long ago, this code behaved differently. There was a significant change in the interface for this procedure. It's not a change that you see in the C signature for this procedure, but it's still an important change in essentially the interface to the procedure. And then finally, I want my code awareness assistant to offer suggested fixes. And so for this code, it's pretty simple, but you can imagine as procedures grow to 100, 200, 600 lines of code, it's hard to pick out just where situations that may be unsafe arise and how those characteristics change as different parts of the code change. And so this is essentially what we're trying to do in this research project. We've built a prototype that does some of this already, and then we've got an additional 2 years of funding from the Navy to carry that out into a full software engineering tool. And so this is what we want the tool to look like at the end of the project. And so we're building it into an Eclipse IDE. So on your left, you have the typical Eclipse C editor. Then we're going to supplement Eclipse with kind of a little panel off to the side that gives you a set of, we call them design notes. These are important characteristics about the code that you're looking at. And one of those characteristics is, when is it safe to call this code? Other information is whether it writes or reads from the pointer variables that it takes as arguments. And there's a number of other properties. You'll see in the middle, we also plan to build a visualization panel within the tool. And the idea here is some of the design characteristics that we mine from the source code may be best shown in a visual format. And for that, we're going to use a visualization rather than just a pure text user interface. This is actually based on technology that I demonstrated and talked about at last year's workshop. I'm not going to go into it in any more detail today, but that video is online on YouTube, so you can check that out. Probably won't be too hard to imagine the role it plays in the code awareness assistant. Right, so the example I've been using so far is just potential null pointer dereference in code. And so you can broaden that to a whole set of preconditions where it may be dangerous to call code in certain contexts, not because it causes a null pointer dereference, but maybe it overwrites memory it shouldn't be overwriting. Maybe it's reading from uninitialized memory. And so I've got a list of kind of things that I would want to know about code or about a procedure if I'm going to call that procedure, or if I'm going to edit that procedure. So the fact that it uses one argument as an index to an array of a second argument, the fact that a procedure assumes that certain globals are initialized, or it assumes that pointers point to the heap, and so it may free those pointers or do other things that assume that those pointers don't point to stack variables. The fact that a procedure allocates memory and therefore should only be used in certain initialization phases in a real-time system, and so on and so on. There's all sorts of kind of facts about how a procedure is expected to be used that were in the head of the author when they were writing the code, but are often not documented in the code. This is partly because C doesn't give you that capability in the language, and this is partly because developers hate documenting all this stuff that really is part of the interface for a procedure, but they'd have to document it using comments, and nobody writes as many comments as they should. And so this is a screenshot of the prototype we've developed so far, and it shows some of the design notes or design characteristics that we mine from software automatically. So up at the top, you can see the unsafe conditions. This is for a different procedure. Null pointer dereferences. We also detect buffer overruns. We also, for any parameters that are pointer parameters, we try to infer whether they're in parameters or out parameters. So in Ada, this is an explicit keyword that's used when you declare a procedure signature. In C, it's not explicit at all and can often be pretty hard to tell just by looking at the code whether a pointer is going to be written through or if it's going to be read from. And then over here, there's another item that we also mine the code for dependencies. So it's another kind of subtle issue in code is if I call a procedure, what implications does that have in terms of adding libraries to my build system? And is that going to add a cyclic dependency to the system that's going to complicate my life when I'm packaging and linking and retesting the system? And so we want to take all this stuff that is kind of implicit in the code, but not at all obvious, and bring it to the fore in an easy to read and easy to refer to panel in Eclipse. Another thing to point out here is you can see up at the top, where's my mouse? We do a comparison between different snapshots of the software. And so as these characteristics are changing, we're kind of highlighting the facts that new things are appearing and other things are disappearing. And so as you, for example, one use case is you check out your code, you establish a base set of design characteristics, and then at the end of the day, you're ready to commit. Go back and do a comparison and see that the design changes or the characteristics that have changed since you checked out that code really match up to your internal picture of how you've manipulated the code. That information's there in the diff, in the source code, but it's hard to see, especially if you're the one who's been editing the code and you kind of have an idea of, oh, well, I'm pretty sure I know what happened. This is kind of an extra expert sitting off to the side saying, you know, you've made a significant change to this procedure. Or is that really what you wanted to do? This is yet another picture of the software development lifecycle. So the kind of thing that we're targeting in this tool is, so in a typical software development lifecycle, you start at a very high level and you make a few very big decisions, concept of operations. What is the system going to do? And then you start working out the detailed requirements and architecture, and you're starting to make kind of more fine-grained decisions, but still pretty big stuff. And then as you get more and more detailed and you work down to the implementation, you're making all sorts of decisions, minute by minute, in terms of what are the variable names, how many procedures should I use to implement this particular piece of functionality, what kind of indentation I should use. At a certain level, those decisions are documented in the source code itself. However, there's this kind of zone. There's this zone that kind of that covers the detailed design and parts of the implementation, maybe even up into the architecture, where you're making a lot of decisions and kind of low-level humdrum decisions, but they're not being documented in the code because they're not things that are typically captured in C, or at least not captured in a very explicit, easy-to-see way. Now, often these decisions aren't all that important in the grand scheme of things, but you do need to be aware of them to really update code and do it in a safe way. Ideally, you would have developers who would document all these decisions in comments or in some documentation off to the side. But as we all know, that doesn't happen as often as it should. And given that they're not documented, these decisions are easily forgotten. And then it's very easy when you go back to make a modification or fix a bug, to add a change or make a change that conflicts with that earlier intent. Now, the nice thing here is often there are hints in the source code so that we can look at the source code and with some static analysis and some looking at the history, try to infer some picture of what the developer originally intended. Right, so I said this just a few seconds ago, but when design decisions are forgotten, the code gets modified by an unaware programmer. And this doesn't mean that the programmer is necessarily dumb. It could just be someone who's new to the project. It could even be someone who's been working on the project for years. It's just they don't understand the code that they wrote 4 months ago because they've been working with other things in the meantime. The new code then violates built-in assumptions and constraints, and even if these aren't big decisions and big design characteristics of the system, I think this adds more of these stepping stones that Gerard referred to in his keynote yesterday. These are little breakages in your system that work as stepping stones so that once something goes wrong, that's yet another link in a chain that may lead to a significant failure. So the consequences, the worst consequence, obviously, is the system fails after deployment. You break the system in a way that's sort of subtle and escapes any testing that happens until after a launch, if it's a spacecraft or after a secure system is deployed to a warfighter, for example. Even if the system problem gets caught before that, the fact that a bug makes it all the way to system testing is still a significant impact on your budget and testing time. And even if the problem is detected earlier, it's still typically a waste in terms of your time as a developer, the time for all the people reviewing your code, the system architect who has to come in and clarify what's going on. And so we're trying to minimize that extra cost. So this is kind of a list of the goals that we're trying to accomplish in the project. So one is to infer design characteristics automatically, so that if these important characteristics are not documented in the code, you can look off to the side and there'll be a little panel that says, oh, you're thinking of using this procedure. Here's some key information that you need to know about. Make sure when you call it, you don't put a null in the third parameter because it's not expecting that. And so this is kind of a quick and instant documentation for code that's not documented. Another goal is to alert a user or a programmer when the design characteristics change in a way that we think is significant. So for example, a change in the procedure interface like I referred to before. Previously, it could handle null pointer arguments. Now it no longer handles them. Maybe there's a change in the performance characteristics. It's now taking a lot more time than it used to, or it's taking a lot less time than it used to. So that's a chance for a programmer to kind of sit back and say, all right, I know what the code change I made was. Let's see what impact that has in some kind of high-level semantic sense. Now, I think the main use case here is a developer working on their own, but I think this is also applicable to peer review or code reviews, where when you go to present your code to a group of peers and get it approved, you can show them the design characteristics of the old version and the design characteristics of the new version. And that's sort of a high-level, easier to read summary of the changes that then supplements the source diff that they're going to be working with in that code. And that that lessens the burden on the code reviewer to actually be able to pick out these significant differences in a big sea of changes in the source code diff. Another goal here is once we've inferred these important design characteristics, we want to make it easier for programmers to actually do the right thing and document things properly. So if the tool detects something that's an important part of the interface of a procedure, we want to make it easy for them to just add with one click to add a section of documentation or add a new assertion to the code. And use the refactoring infrastructure that Eclipse offers so that if programmers were too busy or too preoccupied to insert the documentation before, we're reducing the burden and making it easier for them to actually add that documentation using automation to supplement their work. And then finally, a goal, I'm not sure this will work out, but things like formal methods designed by contract, even static analysis tools, work better if they have annotations of some sort that help them understand what the correct or intended behavior of the code is. And by capturing this information and keeping accumulating a list of important design characteristics, having the users then maybe approving some of those design characteristics as kind of important parts of the interface for a module or procedure, hopefully that will enable stronger and more in-depth static analysis and formal methods. All right, so as I said, we're mining the source code to get these design characteristics. And so far, that gives us a certain amount of information, but mining the source code history kind of is another important piece. And I referred to this earlier in the example. if you've got code where it doesn't handle null pointer arguments, you can look at the history, and if that's a recent change, then that's a big alert and something worth reviewing. And an interesting observation we've come to is sometimes the fact that something has changed is really what matters and kind of what draws you in and to notice something, maybe an unintentional change or something about the code that isn't working right. The fact that previously it handled null and now it doesn't, or previously it made some operation on an array and now it doesn't, is less relevant than the fact that something big has changed here. You need to dig into your code and figure out whether that's really what you meant to do. So this is kind of an architecture for how the tool will work. We take Eclipse, and out of Eclipse we take the code and the various build steps required to build the code, and we give that to a suite of analyzers. So we want to make this a kind of pluggable system so that different static analysis tools can contribute different information. It won't strictly be static analysis. We'll also have specification discovery tools, text analysis, and we want to make it easy for our users to plug in their own scanner. So if there's some particular pattern or design characteristic that you've implemented a check for using grep or Perl or something more sophisticated, we want to be able to plug that in, and then we'll track that and check it in history and expose it to the programmer when it comes time to review their changes. All that information gets thrown into a project database, and then we record that in the history too. And then before showing it to the user, we have to apply a significant amount of filtering and transformation so that the results are intelligible to a C programmer. So if you look at kind of the internal representation that a static analysis tool keeps, it's a pretty intimidating, often pretty obscure set of information. And so we already do this as part of our static analysis tool report generation. We're going to have to do something similar in this tool. Oh yeah, and off to the side, kind of extra features. As we're observing the changes that are being made, we're building up our own history. We don't want to depend on just that history, so we want to also draw information from the version control repository to get snapshots from previous versions, so you can compare design characteristics across across a team, so that one developer can use the characteristics collected on another machine, and so on. And we also hope to pull some of these design characteristics from modeling languages like UML. We have an OCL constraint on a particular piece of the system. Bring that in as one of the design characteristics and then compare it to what we actually observe in the code and see if there's a discrepancy. How much time do I have? Yeah. All right. So the way the tool works is similar to the kind of flow you see in compilers and static analysis tools. Of course, take the code. You start with break it into a set of abstract syntax trees, and then from that you build an intermediate representation. And then usually compilers will turn that into machine code. Editors like Eclipse will mine that intermediate representation for their syntax coloring. For static analysis, usually there's an additional analysis step where we take the intermediate representation, which is mostly structure, and then we pull out scenarios and try to pull out semantics. So, what are the effects of a given procedure, or what happens when you follow this block of code through this if branch and then through this loop? And then, so the tools like Code Sonar, and I assume Clockwork and the other tools in this space, then use that information and generate a set of warnings. In the Code Awareness Assistant, we're taking that same set of information, but instead of generating just a list of warnings that apply to the code, we're spitting out design observations. And because of the way that the user is going to interact with this, we can show different information. We can show things that we wouldn't bother a user with because it doesn't rise to the level of a warning, but it's maybe worth popping up when they're working with that code just because they should be aware of it. Similarly, there's things that we can't show because it's too tentative, whereas in a warning, typically you've already made a conclusion that it's worth reporting. So certainly one of the main challenges in this project is going to be kind of a user interface challenge. So we don't want to take up too much of an Eclipse developer's screen. They're going to be focusing on their code and debugging, and they're going to have limited cognitive cycles to dedicate to reading our panel. And so we really want to focus on what information is valuable to a coder. And so one thing we want to do is drop any information that's clear from the code. We don't want to be a redundant source of information for something that's for the information they're already getting from their code editor. Another challenge will be summarizing things and reporting them in plain English as opposed to some kind of internal logical representation. And then an interesting challenge that's come up in the initial prototype is static analysis tools track a huge amount of information about all sorts of weird corner cases. This is especially relevant in C because there's so many ways to shoot yourself in the foot. So for example, another problem with this swap procedure is potentially, what if you pass in for the X argument, it's one past the end of an integer array. Then you're going to have a buffer overrun when you do the swap operation. Is that worth reporting? Well, I don't know. I think that's sort of maybe implicit in the interface, that you shouldn't throw in pointers that don't point to valid locations. But it's certainly a problem that can occur in C, and it's definitely information that we have from the semantics that we've collected from this procedure. An even more obscure example is, what if someone's actually passed in a pointer to a car and you don't have sufficient space to actually do the swap? Now this is kind of really abusing the world of C, but compilers will let you do this, and in some cases you run into code that kind of plays these games and tries to move pointers around in types that don't really correspond to the space. And so if you just take a raw dump of the things that a static analysis tool worries about and show it on the screen, you're going to get a long list of kind of these pedantic corner cases. One of our jobs is going to be to filter that information, sort of pull out the things that are kind of common enough and I guess salient enough for in a typical case to be worth showing. Right, so I mentioned earlier that I'm looking for engagement here. So one thing I'm looking for is, what are the program characteristics that are useful to you in the projects that you're working with? You know, what are things that are not covered by existing tools, that are not being detected by tools in your tool chain, you know, specifically to the spacecraft flight software domain. Another source of engagement is, in 9 to 12 months, we hope to have a workable prototype that you can actually run on your desktop and use as you're writing code, if you happen to be using Eclipse. And so at that point, we'd like to be able to deploy it to a set of early adopters and gather feedback and suggestions and hopefully get some information about what's working, what isn't working. So I've been talking about design decisions and making sure that any changes to code are consistent with the kind of implicit or previous intent of a developer. And I wanted to spend a little bit of time saying this is not the only way to deal with this problem. There are other approaches, some of which have been mentioned in some of the other talks. And so I wanted to mention a few of them so that before the tool here is ready for you, you have some other techniques that you can use. So a big one here is using assertion. So it's a great way to add in a check that any assumptions in your code are actually valid at runtime, and it also works as documentation to developers who come along and read that code. And then in addition to assertions, leverage the other things that the C compiler tool chain gives you. So there's all sorts of type checking that GCC does, things like enums and various ways of structuring your code, maybe using macros to take care of generating boilerplate instead of maintaining that by hand, just to make it as hard as possible for you to insert one of these discrepancies or new code that disobeys kind of the existing constraints. And then another kind of emerging approach is autocoding, where you don't write the code at all. Instead, you have kind of a design stored in some format and then generate code automatically from that. And that can be kind of the heavyweight model-based design approach, or it doesn't have to be heavyweight. You can just take an XML structure and use it to spit out message parsing code or structure information. And that helps reduce the possibility that somebody making a change in one spot violates some assumption that somebody made in some other spot in your code. And then finally, another thing you can do to help reduce these problems is scan code for design violations aggressively. Gerard mentioned enabling compiler warnings has a very big effect on code quality. And then you can supplement those compiler warnings with simple grep awk Perl scripts, like the Fraunhofer talk a few hours ago. It's not that hard to insert that into your compiled tool chain. If there's a significant problem, a pattern that comes up often, just write a little script and stick it in, and that's one of the additional things you check. And then finally, if you are using static analysis tools at your organization, as far as I know, they all come with fairly sophisticated customization facilities. So learn those APIs and scripting languages and take advantage of them to really identify kind of the things that are bugging you and that are coming up in your particular application and that aren't being addressed by the built-in checks. And then more generally, we're engineers. We like to manipulate embedded systems or whatever target system we're working with. Apply that desire to re-engineer and improve and optimize to the software development lifecycle itself. And don't be afraid of going and writing a few scripts or something to help increase your quality or testing efficiency. So that's about it. I just wanted to introduce the project, the Code Awareness Assistant. We're hoping to infer design decisions from code and then document them, warn you when you're going to make a change that's going to violate one of those design decisions. I'm looking for engagement from the community, both in terms of kind of requirements and ideas, and early adopters down the road when we have something that can be used. And then I want to encourage you to both use this tool and kind of take the general approach of automating, leveraging automation in your software development. And so Curtis has stepped into the room. I just wanted to highlight him. He's going to be the one manning the booth if you have questions about Code Sonar. If you have questions about Code Sonar's use in this project, I can field those, but Curtis is really the best to talk about the features and the latest and greatest things that the product itself has. So, questions?
Let me quick for you. Is your email address on these charts?
I think it's on the first slide.
That would be good because we're going to post these, right, on flightsoftware.org. And if somebody wants to be an early adopter, did you have a question? Let me get your microphone. Yeah, maybe. Yeah. Could be. Yes.
So what CM tools are you integrated with already? And also, I'd caution against depending upon the users to employ CM tools to capture a history. It might be good just to ad hoc it, from my experience.
Yeah. So we, for the immediate term, we're going to be working with Subversion, we think. Partly because that's what we use internally. It's sort of fairly well established. I think the general approach will work for basically anything where as long as you're saving code in a way that can be recovered later, you should be able to integrate with the history features that we're going to need and build into our tool. Regarding not depending on it, we're trying to architect the system so that if you don't have a CM tool for some reason, God help you, then you'll still get the benefits, and we'll offer some kind of sharing repository through other technical means.
Sorry, I used to be a program manager.
Yeah.
Scary thing to say. Any other questions? Nope. Thank you very much.
Okay.